This video covers section 5.4, which is titled Comparison Test, and in it we're going to take a look at a new test for actually several new tests, both the comparison test and the limit comparison test, which are tests for telling if a series converges or diverges. And the only tests we've covered so far, you'll remember, are the integral test and also the test for divergence, or the divergence test. So again, this chapter 5, we're exploring how we tell if a series converges or diverges. So this is the next test in the sequence. No pun on words intended there. So let's go ahead and jump in by looking at an example. Let's consider series 1 over 3 to the n plus n. And let's start by asking two questions. Let's say, okay, those tests that we learned in the past, the divergence test and the integral test, can we use those? Would those be a good idea here? Because one of the ideas, so when we have our next test, the third test, I'm not gonna tell you use this test, use this test. You're gonna need to take a series and determine on your own if it converges or diverges. And almost the first thing you should ask yourself every time is, will a divergence test work? And because if that's the case, then you can just stop right there. So remember, for the divergence test, we want to take the limit of the sequence of terms as n approaches infinity, and we want to see if it equals some constant other than 0, so that we are continually adding a constant to the sum, which means it's never going to converge. Now, if we plug in infinity here, what do we get? We get 1 over infinity, which of course we know to be 0. So what does that tell us about the divergence test? Yeah, that tells us that the divergence test is inconclusive. So we can just say the divergence test is inconclusive. So we move on. That doesn't work. That's all right. It didn't take us very long to try that. So next, let's talk about the integral test. So we would be integrating 1 over 3 to the n plus n. Can we integrate that? Can we integrate this part right here? And hopefully you agree that the answer is no. That's not something we know how to integrate. So the answer would be no, we cannot integrate f of x equals 1 over 3 to the x plus x. That's not something we know how to integrate, so we can't use that test. So that leaves us with needing something new. And so the idea here is that we're going to use the comparison test, and we're going to compare what we had, 1 over 3 to the n plus n, with 1 over 3 to the n. And so this is what the comparison test is. Theorem 5.11. It says, suppose there exists an integer n such that a to the n is greater than or equal to 0, but less than or equal to b to the n, for n greater than or equal to n. If b of n converges, then a sub n also converges. Those series, right? So if the series of b sub n converges, then a sub n converges. So what's this saying? If we have some series, b sub n, that we know converges, we know this series converges, and for every term in that series, so b1, b2, b3, b4, if for every term in that series, each term, so b1 is greater than or equal to a1, and b2 is greater than or equal to a2, and b3 is greater than or equal to a3, then we know that that series of a sub n must also converge, because the terms of b sub n are going to add up to something, right? They're going to add up to something. And if those terms are all bigger than a sub n, then that means the series of a sub n must also add up to something. Now, on the flip side, let's say, for example, that we have some series, some different series, B sub n, that diverges. And term by term, our series that we're trying to figure out if it converges or diverges is bigger than each of those terms. So A1 is bigger than B1, and A2 is bigger than B2, and A3 is bigger than B3, and so on. And we know, again, that the series of B sub n diverges. So if you add up all the B's, B1 plus B2 plus B3, they diverge. And that means that the series of A sub n must also diverge, because it's going to be an even bigger series, right? Or it's going to have even a bigger sum. So let me say that one more time. If we have a series that we know converges, and all the terms of that series are bigger than term by term than all the series of our other series, then that other series must also converge. In other words, the sum, if B sub n has a sum, then A sub n must also have a sum. And then on the flip, if all our terms term by term are bigger than each of the terms in our divergent series, then the other series must also diverge. So let's see how this works. Before we do an example, generally speaking, there are two series that we're going to compare to. We're going to compare to those series that we've been studying. So the geometric series. You remember its form. It looks like A times R to the n minus 1. And then the other one we're going to look at typically for the comparison test is the P series. So our P series, if you will recall, looks like 1 over n raised to the P power. And so, do you remember what the cases were? Remember, these are two series that you need to have memorized. So, what value of R causes a geometric series to converge? You remember that one? Geometric series converges if the absolute value of R is less than 1. So less than 1. If R is less than 1, actually let me write if the absolute value of R is less than 1, then it converges. And then if the absolute value of R is greater than or equal to 1, then it diverges. Okay, and then for the P series, do you remember what makes a P series converge? Depends on the value of P. So if P is greater than 1, then it converges. And then on the flip side, if P is less than or equal to 1, then diverges. So let's take a look at some examples. And the key to doing these is just being able to tell what to compare with. That's one of the big keys. So, all right, so let's look at example 1a. Using the comparison test, determine if the series converges or diverges. And we have 6 to the n over 5 to the n minus 1. And if you look at that, 6 to the n and 5 to the n are having the most impact on this. The negative 1 has very little impact. So it would be nice if we could compare it to 6 to the n over 5 to the n. Now how do we think about doing this comparison? This is kind of just you have to do this reasoning I'm about to talk about in most of these problems. So let's talk about this. If you compare these two, the numerator is exactly the same. What's different is the denominator. And so you want to think about, well, which denominator is bigger or smaller? So if you look at the one on the left over here, if you look at the one on the left, we have 5 to the n minus 1. And because the other one is 5 to the n, the one on the left is 1 smaller than the one on the right. So in other words, we can say and let's even make a little note here, this one on the left has a smaller denominator. So why is that important? Well, if it has a smaller denominator, then that means we're taking and dividing by something smaller in every term. So if you divide by a smaller number, that means overall you're going to have something bigger. So the thing on the left is going to be bigger than, each term on the left is going to be bigger than each term on the right, because the denominator is smaller on the left. Now, why is that important? Well, the one on the right that we're comparing to is actually geometric, right? So we have 6 over 5 to the n. That looks like this geometric series that we're familiar with, and we know that geometric series converge or diverge based on the value of r. Now, what's r in this case? Right? R is 6/5. So is this going to converge or diverge? Well, hopefully you said that it's going to diverge because r is bigger than 1. So what we can say, and remember, when you're doing these problems, you need to explain your result. You can't just say converge or diverge. That's not going to suffice on the test. So this is the way I write these out every time. You're going to notice a pattern that I use for all these comparison test problems. So we make our comparison. Our term-by-term comparison says that our original series, the terms are bigger than our compared terms of the series, than the terms of the series we're comparing to. So now what we can say is, and this series, the geometric one, 6 over 5 to the n, is a geometric series, right? It's a geometric series. You always want to talk about the series we're comparing with r greater than 1, which does what? Does it converge or diverge? It diverges. So then we can say our original series, 6 to the n over 5 to the n minus 1, also diverges by what test? By the comparison test. Gotta explain it. So hopefully that made sense. We're going to do 2 more problems here. Let's move on to B. Okay, so in example A, it was easy to find a comparison because we could just take away the minus 1 and it gave us geometric. Now, this one's a little bit more difficult because we're adding something to the numerator and we're adding something to the denominator. And we know that if we just had n squared over n to the 4th, that would reduce to 1 over n squared, which looks like not geometric, but it looks like our p series, right? The problem is, though, because we're adding something to both the numerator and the denominator, we can't just compare because we don't know which one's bigger. And so, I mean, we can't just get rid of both of those because we don't know, like we have no way of comparing whether n squared plus 2 over n to the 4th plus 5 is greater than or less than. We don't know whether or not the one on the left is bigger or smaller than the one on the right. So we have to be a little bit more creative for one like this. And the way we're going to attack this is we're going to rather think about splitting up our originals. So if we take n squared plus 2 over n to the 4th plus 5, what we can try doing is just getting rid of the denominator plus 5. So that would leave us with n squared plus 2 over n to the 4th plus just n to the fourth. Now, if that's the case, then which one has, so the one on the left then, the one on the left now has a bigger or a smaller denominator? This has a bigger denominator, right? So that means for each term, it's dividing by a bigger number. Now, if you're dividing by bigger numbers, that's actually going to make things smaller. So term by term, the left side is going to be smaller than what's on the right. So we better hope then that what's on the right converges, right? Now we don't know yet what we have on the right, so we need to simplify this. The advantage of getting rid of the plus 5 on the bottom is we can now separate this into n squared over n to the fourth plus 2 over n to the fourth. And this simplifies to 1 over n squared plus 2 over n to the fourth. And the beauty of that is now we have the sum of 2. If we were to make these into series, if we were to add all these terms, both of those series would be convergent P series with P greater than 1, right? P series, if P is greater than 1, then it converges. So we can say this: both one over n squared and 1 over n to the fourth. We can add a 2 with it, right? We can pull the 2 out. That doesn't matter about the P series. We can say both are convergent P series, right? So what does that mean? If you add two series that both converge, so they both have a sum, if you add them both up and they both converge, then what can we say about the sum of those two series? Well, then that must have a sum, right? Then our series n squared plus 2 over n to the fourth must also converge. Thus, our original series, n squared plus 2 over n to the fourth plus 5, must also converge by the comparison test. Now that's it. And the reason why this worked, again, is because term by term, our original series, each term by term, was smaller than the terms of the sequence that we were comparing to. And the sequence we were comparing to converge. Remember, you got to be less than a convergent series, or you got to be greater than a divergent series. All right, let's do one more here. One more. So example C, we have n over n squared minus cosine squared n. And the cosine squared n just kind of complicates things. So it would be nice if we could compare n over n squared minus cosine squared n. If we could compare that with just n over n squared, because we know that n over n squared reduces to 1 over n. And if you take the sum of that, what series do we have? The series of sum from n equals 1 to infinity of 1 over m, that is the harmonic series. And the harmonic series we know diverges. So what do we have? I'm going to do this one more time, this comparison deal. Is our left denominator bigger or smaller? We have you're going to be subtracting cosine squared. Now cosine can be -1 or +1, but when you square it, it's always going to be 1. So we're always going to be subtracting 1 or less from what we have. So this is going to be a smaller denominator on the left because we're subtracting something, a positive amount. So this is a smaller denominator. If it's a smaller denominator, what does that mean about what we have on the right? I mean, what do we have on the left? If we're dividing by something smaller, that means it's going to be something bigger. And I'm going to add an equal to here because it could be equal to, because cosine can be 0 as well. So if cosine is 0, then those two can be equal. But it doesn't have to be just greater than. It could be greater than or equal to. And so that's what we have. This works out. Term by term, our original series is always going to be at least as big as the series we're comparing to. And that series we're comparing to, we know, is the divergent harmonic series. Right? So that means that our original series, n equals 1 to infinity of n over n squared minus cosine squared n, must also diverge by what test? By the comparison test. And that's going to do it for this video. Now, you may be asking yourself, well, what happens when these little inequalities that we have to do to make the comparison test work don't go the right way? Well, that's where our other test comes in. That's the limit comparison test. So we'll go ahead and take a look at that in the next video. All right. Thank you for your time.